Thanks, everyone. Thanks for the opportunity to speak. So what I'm going to talk about is joint work with Mikołaj, Frączyk, and Amanda Wilkens. I stress that it is ongoing work, which is my way of saying that the preprint is not yet available. But the proofs are written in a somewhat rough kind of shape, which means that the theories are true. So, but before I get into what we actually showed, because it's going to be a long road, I wanted to give some motivating corollaries. So for this talk, G will typically denote a higher rank semisimple Lie group. So for instance, SL3R, but also SL2R times SL2R. The theorem also covers other cases. If you don't know anything about Lie groups, that's fine. You'll still be able to follow the talk. So here's some corollaries of our result. So the first one is an immediate corollary. Any lattice in such a group has fixed price 1. So it has been known, going back to Damien's original paper, that certain very special lattices in these groups have fixed price 1. And we're able to extend this now to all lattices via a completely different method. So it's the previous proof relies on the existence of very special generating sets, and these don't always exist, whereas our proof is much more geometric. So the second corollary, this is not immediate, but it follows by applying a theorem that I proved with Mikołaj, that if you take any sequence of torsion-free lattices in such a group with volume tending to infinity, this is automatic, then the rank gradient vanishes. So the rank gradient here, rank means minimum size of a generating set. So we take rank minus 1, and we normalize by the volume, and this vanishes. Okay, so special cases of this have been known, but now we extend it. In a paper of Mikołaj, Nick Nikolov, and Sahik Gelrander, this is posed as a provocative conjecture. So I don't know if that means that our solution is also provocative, but yeah. So please keep in mind these results as I'm talking about all of this point process nonsense. So I just want to say something about how one of these results comes about, and that is the idea of inducing an action from a lattice. So suppose you have a lattice, which I remind you, this is a discrete subgroup such that the quotient carries a finite invariant measure. Whenever you take a free PNP action of a lattice, then you can induce it to an action of the ambient group. So I'll say something about how you actually do this later on. But I just want to say that this is an example of what I'll call a marked point process action. So what we're going to do is we're going to define the cost of arbitrary marked point process actions. And it will satisfy the following relation, that the cost minus 1 for the induced action is equal to the cost minus 1 for the lattice action normalized by the volume. And in particular, fixed price for point processes for this group implies fixed price for its lattices. So this is how this argument is going to go. You may recognize that this thing on the right-hand side looks remarkably like the terms which appear in the definition of the rank gradient. This is not at all a coincidence. Okay, so I just want to make one more quick aside. So something I observed with Mikołaj is that every PNP action of a locally compact group is isomorphic to some point process action. That is to say, point processes are not some special class of actions, which you need to be like a wizard at probability theory in order to understand. On the contrary, they are the only game in town. Okay, so if you're the sort of individual that fancies yourself as someone interested in PNP actions of locally compact groups, then I hate to be the bearer of bad news, but you care about point processes. Yeah.
Just to make sure I understand, you're saying that you can always find an action of like a gamma on something and then induce it up to get one of these.
No, I'm saying that every PNP action of the ambient group is isomorphic to a point process. Not necessarily one of these lattice ones. I mean, definitely not one of these lattice ones in general.
What's a point process action?
That comes on the next slide. I have to explain all of these steps. Yeah.
What to say is you should learn what's coming.
Yeah, exactly. You can't avoid the point processes. At least you can't hide from it.
They're all
Okay, so now let me outline the rest of the talk. So I have to explain what point process actions are, obviously. I have to tell you what their cost is. I'll give you some fundamental properties of this cost. And then I'll introduce the new objects. So one of them is called the PPVT, and one is called the IPVT. This is the exciting part. And then I'll give you a sketch of how the IPVT's strange properties give us fixed price. So this is actually the first time this is being spoken about publicly, although we did a bit of a soft launch last week. I explained this proof to some people like Łukasz, Tiani, Damien, and I think they'll agree that this IPVT is very much a strange beast. Okay, so let's finally get into it. So here's the general setup for point processes. So for now, G is going to be a locally compact second countable group. This is the right context to talk about point processes. Some of what I discussed requires the group to be unimodular. Some of it doesn't. Let's just say unimodular anyway. And these groups, they admit a proper left invariant metric and a left invariant Haar measure. So I fix these. Proper meaning that closed balls are compact. All of these things are basically equivalent. Having such a metric, having a Haar measure, being locally compact second countable. So additionally, I'm going to assume that my group is non-compact. In other words, its Haar measure is infinite, and also non-discrete. So the Haar measure is atomless. This is nothing against compact groups. It's just that the particular questions that we're going to ask will be trivial for those. And it's also nothing against discrete groups. It's just that we're specifically trying to study non-discrete groups. So good examples to have in mind are things like SL3R, the isometry group of the hyperbolic plane, or TD times ORTD, and also R squared, because that's the only one I can draw pictures for. So what are the point processes at last? They are random subsets of your group. Okay, so let me be a bit more formal about this. I introduce something that I call the configuration space. This is the space of locally finite subsets of your group. Okay, so you think of it as some kind of discrete scattering of points in the group. There is a natural shift action on this space, just shifting it as a set of points. And a point process is a random element of this space, or if you prefer, a probability measure on it. I'm going to stick to random variable notation because it is absolutely superior in almost every context. We say that the point process is invariant if G times pi has the same distribution as pi, right? A priori, G times pi, when I shift it, I get some other point process. And what I want is that it has the same distribution. Okay, so it's statistically homogeneous in that sense. Again, or if you prefer, it means that we have a PMP action for this shift thing. Okay, feel free to stop at any time for questions or whatever. So I said that this was the configuration space, and it is a nice space. It's a Polish space, but I don't want to talk too much about the metric, but I will say something about its measurable structure. So whenever you have a subset of the space, U, you can look at its associated point count function, right? Just counting the number of points that this configuration has in that little window. And so I declare that all of these are going to be measurable. In particular, if I have some point process pi, then I can look at the number of points pi has in some set U, and that is a textbook example of a random variable. And so we can start talking about its expectation. So we define the intensity of an invariant point process to be the expected number of points that you see in some window U, normalized by the volume of that set. Okay, so the idea is that that if I look at this function, so U mapping to this expectation, then that's essentially defining a Haar measure on the group. And so when I divide by lambda of U, I end up with something which is independent of my choice of U. So some examples. So the first of these is lattice shifts. So if you have a lattice, then this space of cotets, those are configurations, right? A lattice is a discrete subset of the group, and so is any shift of the lattice. And this is defining a point process on the group. More concretely, you can think of it as you fix a fundamental domain for your lattice, you pick one point at random from that, and then you shift the lattice by that. That argument also explains why the intensity of lattice shift is 1 over the covolume. So the next example is the Poisson point process. So this is the most important example. If this is your first time seeing this, you're probably not going to completely get it. But if you just have this kind of vague idea in your mind, so if I have a countable group, I can specify a random subset of it just by doing IID coin flips. And the Poisson point process is the way that you do the analog of that for a non-discrete group. Okay, so if you just have that image in your mind, you should be fine. It's a totally random subset of the group somehow. But so more formally, I say that a point process is Poisson with intensity T if it satisfies the following two conditions. So the first of them, shock of all shocks, is that the point counts should be Poisson distributed. Okay, so Poisson with parameter T times the volume of the set. Explicitly, that means that the probability you see K points is given by this formula. So maybe you forgot why the Poisson distribution is so important. Just as a quick way to catch you up.
For every measurable A?
That's right, yes. For every window, you see Poisson many points. So the way that you get this Poisson measure on the natural numbers is you basically take like the power series for the exponential function and you normalize it term by term. So the exponential function is obviously a very special function. So maybe it's not so surprising that this measure is also very special. If you don't like that condition, we have the next one. So if I take disjoint subsets of my group, then the number of points that you see is independent. Okay. And so it is essentially a theorem of blending that both of these properties are equivalent. So you can just think about the second one if you want. What you observe in disjoint sets in the Poisson point process is independent, and it is the only point process with this property. Any questions about the Poisson?
Can you remind me, or is there a nice probabilistic way of sampling this on R, the point process?
It is extremely easy to sample from this process. If you can pick one point at random, then you can sample from this.
Yeah.
Yeah. So what you do is you sample Poisson many points, and then independently you put them down uniformly at random, independently and uniformly at random. So what I've just described is essentially how you construct this process. If you want to learn more about it or any other aspect of this talk, I'm happy to explain it to anyone, but we have very little time, so I have to kind of blitzkrieg through this. So let me give you some facts about this Poisson point process. So I am actually going to write down the PMP action associated to this. So this is the Poisson point process action for the Poisson point process of intensity T. It's ergodic if and only if the group is non-compact. So if the group is compact, then it's kind of manifestly non-ergodic. And if the group is non-compact, then you prove this basically the same way you prove the Bernoulli shift is, well, mixing. It's essentially free if the group is non-compact, that is, that it has no symmetries almost surely. This is not a fact that we'll use, but I advertise it. It has spectral gap if and only if the group is non-immutable. And it's a result of Amanda Wilkens that this is actually only one action up to isomorphism. So for probability theory, it is still important to consider the Poissons of different intensity, but as an abstract action, it's just one thing. So what's next? I have to explain to you what cost is. So here's the idea. The cost of a point process is the cheapest way to connect it up. So connecting it up means that we're going to look at an object called a connected factor graph. This is the analog of a graphing. And cheapest means we'll take the infimum of their average degree. Okay, so I have to explain what these things are. And I should also point out that there is a more sophisticated way of understanding what this cost is for point processes. And it involves learning a little bit more probability theory. And we're essentially taking the cost of an associated equivalence relation, something called the Palm equivalence relation. So if you really want to understand what is going on in this project, you'll have to learn what this thing is. But just to give a sort of course overview of what we've done, you don't need to. So to explain what the concept of a factor graph is, I'll give you one of the most fundamental examples, and then I'll give you the general definition. So the distance R factor graph on a point process is the following random graph. I'm just going to connect pairs of points if the distance between them is less than R. Okay, so this is a graph whose vertex set is well, it's random. It's a sample from the point process, but it's a graph that somehow lives on the point process. So the two things to take away from this is that this is deterministic given the input. Okay, I give you the set of points, and then to construct this graph, all you need to do is measure the distance between edges. You don't need to run around and walk or take balls out of urns or any of these strange things probability theorists do. You're just measuring edges, the distances between points. It's also equivariantly defined. So if I shift my set of points, then the graph also shifts in a natural sense. And this is precisely because we use the left invariant metric. Okay, so these properties are what we're going to abstract in the following more formal definition. So let me introduce yet another space. This is a space of abstractly embedded graphs in my group. So of course, a graph has a vertex set and an edge set. I want the vertex set to be a configuration and the edge set to be a configuration in G times G. So I want this E to really define a graph structure on V. So in other words, it should be symmetric and contained in times V times V, contained in V times V. So there is a natural shift action on the space of graphs abstractly embedded in my group. And what I call a factor graph is a measurable and equivariant map, fancy G, into this space such that the vertex set of G of pi is pi. Okay, so it's a graph living on the point process. And you can ask, what do these factor graphs tell us about the group? And vice versa. But this is a crucial definition. So I don't know, are there any questions about this? Or sorry?
Are there self loops?
In this definition, no, but you can change the definition to, you can construct whatever space of graphs you want, like directed, labeled, anything. Yeah.
Where's the invariance essentially?
You mean that it's that this factor graph should be equivariantly defined. So
You have some process on the, I mean, you have some measure on the configuration space on both sides.
that's,
You want,
I mean, so pi is the invariant point process, and I'm putting the graph structure on pi.
and your point process also gives a measure on like G, M of G cross G.
Yeah, I mean, you could consider just what the edge set of this graph is. Like you could just view that as a random graph if you want.
But then it would automatically be invariant because like if you're mapping
Yeah.
invariant.
Yeah, exactly. Yeah.
I have.
So the graph that the random graph that you construct in that way will be an invariant random graph.
Okay, like the equivariance issue that it could be invariant.
Exactly. Yes. Yes.
Okay.
So the distance R graph is an example of factor graph.
Exactly. But it is not the only, I mean, that's a very natural one that you would consider. The study of that graph is basically the subject of continuum percolation theory. Like you can just study that one graph of the Poisson point process and, get a career. Okay. Any further questions about factor graphs? This is a crucial concept. So let me give you some other quick examples. So the existence of connected factor graphs on a point process, which look like K graphs of countable groups, is essentially the question of measure equivalence. So I don't really want to spend too much time on this, but if you think about it for a while, what you can show is that a group is immutable if and only if its free point processes emit Z as a connected factor graph. And you can also show that if your group has property T, then the Poisson point process specifically has no connected factor graphs which look like Cayley graphs of countable groups. Okay, so yeah. So now we have our graphings. I need to now explain what the average degree is. So suppose you sample from your point process, you see this random scattering of points, and you have a factor graph. So you see this graph structure on the set of points. Now there's a natural way to talk about its average degree. Don't think too much about this formula, it's a bit ugly. But the idea is that, well, when we took intensity of the point process, we looked in this little bounded window and we just counted the number of points that you see in expectation. Now we want to do basically the same thing, except we weight the points by their degree in that graph. Okay, so stated this way, I don't know how natural this definition is for average degree, but if you learn that palm theory, this probability theory stuff, then there is a better way of doing it, but this will work for this talk. At last, we can finally get to the cost. So the cost of an invariant point process is defined by the following formula. So the cost minus 1 is equal to the infimum over all connected factor graphs. And you take half the average degree and you subtract the intensity. Okay, so this kind of normalization might seem a bit funny, but well, it's the way that you have to do it in order to get an isomorphism invariant. If you learn this palm theory, then there is a way that you can think about this formula. So for equivalence relations, you have this induction formula of Damian. It's also known as the cost of a complete section. And you can view this formula for what's called the palm process as a kind of infinitesimal version of that. So it really is a natural formula. I know some people in the audience dislike this formula, but it's true. So, okay. But in practice, the way that I think of it is just look at connected factor graphs and take the infimum of their average degree. Okay, all good? You seem happy. I don't know.
I just find it funny that someone dislikes the phone.
It's, I mean, I don't want to, name names or anything. It's not naming names. It's pointing a finger. It's a completely different exercise. Okay.
So maybe for people who are thinking, so there's, correct me if I'm wrong, but there's an equivalence of categories between the category of graphing the PMP actions of G and the category of factor graphs of point processes, invariant point processes of G.
Maybe we can. we can figure this out. Graphs are the exact same thing as graphings for this corresponding equivalence relation. So yeah, I don't know if that is an equivalence of categories.
All right, we can discuss it all, so.
Sure. Okay. So one thing that you can check is that the cost minus one scales with the choice of your harm measure. Okay, so it's really cost minus one is the good invariant. When you're talking about countable groups, you have a canonical way of choosing your harm measure for all of them simultaneously. Whereas for arbitrary locally compact groups, you don't have this luck. Oh, so some of you recognize this word maybe. I want to give you a list of prices of groups. Okay, so immutable groups have fixed price one. Something I proved with Mikołaj is that groups in the form G times Z have fixed price one. This is not really the point of their paper, but it is a consequence of something proved by Quinton, Damian, Andrew Marks, and Robin, that the isometry group of the hyperbolic plane has fixed price, as well as the automorphism group of a regular tree. And something I observed with Damian is that Nereson's group also has fixed price one. Okay, so 22 minutes in, I can finally state what our theorem actually is. So we add to this list. Higher rank semi-simple Lie groups have fixed price one. The argument also applies to other groups. So for instance, the automorphism group of a tree times the automorphism group of a tree, but also AUT-TD times SL2R. If you're interested in exactly what this class of groups is, then I can explain some other time. It's just a little unwieldy to explain. Okay. So now I want to go back to marked point processes. This is one of the first things that I mentioned, that when you induce an action of a lattice, you end up with something called a marked point process. So let me explain what these are. Once again, I'll give you an informal example, and then we'll see, a proper definition. So this is what I'll call the heads tails IID of a point process. So the idea is that you're first going to sample from the point process. This gives you this random scattering of points. And then for each one of those, I want you to independently toss a coin. The coin comes up heads or tails, and you color the point according to how this coin toss comes out. Okay, so strictly speaking, this is no longer a point process as I've explained, but it's a kind of marked or colored or labeled point process. It's some subset of the points, subset of the space where every point has like a label associated to it. So let's be a bit more formal about this. I introduce yet another space. I call this the marked configuration space. I have this slight abuse of notation, but it will make sense when the next slide shows up. So this is the space of 0, 1 marked configurations. So formally, they are configurations in G times the unit interval. And this uniquely marked means that each point only receives one label, right? In the previous example, you toss a coin, the coin comes up heads or tails, but it doesn't come up heads and tails. You only get one label. That's formally speaking what this uniquely marked condition means. So a marked point process is a random element of this space. And all of the other definitions that I made, they apply equally well to marked point processes. And so now if you have a point process, now I'm giving you an example of one of these marked point processes. Its IID marking is the marked point process given in this kind of, again, exponential notation, which is just pi with independent uniform 0, 1 random labels. Concretely, the way that you can think of it is just like what we did on the previous slide. You sample from the process, and then each point tosses now countably many coins independently, and that's the exact same thing as this object. Okay, I use this kind of exponential notation to evoke the Bernoulli shift. So this is really, it's really the Bernoulli extension of this action. But yeah, so sometimes instead of saying IID marking, I'll just say the IID of the point process. This is a bad habit that I got into with Mikołaj, but I'm kind of stuck with it now. Questions about this concept? So there is another example. So yeah, I started off saying that you can induce actions of lattices, and this gives you an example of a marked point process. Truth be told, I didn't really finish this slide, so I don't know. I can explain it to you afterwards if you're interested in how this goes. But inducing an action from a lattice naturally gives you a marked point process. So now I need to tell you some fundamental facts about this cost. So the first of these is that it can only go up under a factor. So if I have phi is some measurable and equivariant map of the configuration space into itself, then when I apply phi to a point process, I end up with another point process, sorry, a invariant point process. And you can ask how their cost is related. And it turns out that the cost can only increase. So the way that you kind of think about this is that, well, phi of pi is somehow a simpler process than pi. I can produce it from pi. And so any connected factor graph I have of phi of pi, I can somehow pull it back to pi. And because cost is defined as an infimum, this is the reason why you would expect this to be the inequality. That's sort of the general idea of why this is the way it is. So more generally, if phi n of pi is a sequence of point process factors converging weakly to a process epsilon, then the cost can only increase. Epsilon is the Commonwealth British English way of saying it. Apparently, I should be saying what epsilon or what? Oops, oopsilon. I don't know about that. So epsilon. So I don't want to say too much about what this weak convergence really means, but this is. I mean, basically, it means that this sequence of processes looks more and more like the limit process epsilon in a certain statistical sense. Okay? But again, the cost can only increase in this situation. And we say that pi weakly factors onto epsilon in this. Okay. So something I proved with Mikołaj is that if you have an essentially free point process, then it weakly factors onto its own Bernoulli extension, its own IID marking.
Okay, it's a trivial but not
You can ask for your time.
I'm just so for your definition, since you insist on everything being locally finite, can you is a trivial action on the single point space isomorphic to a point process?
So when I said that every action is isomorphic to a point process, strictly speaking, I should mean pre-point process, but otherwise you can consider it as every non-free action is kind of a point process on a bundle of the homogeneous spaces. So strictly speaking, this is how this goes.
Okay.
I mean,
the way it's yeah. So right now, it's not compact. This space.
No, absolutely not. Yeah, I guess you could also consider the empty point process, right, for the trivial action.
Perhaps maybe that's that way. Okay.
So if you piece together these two facts that I just told you, then the cost of a point process, a free point process, is equal to the cost of its IID marking. And I want to stress that this is not at all obvious. This first appeared in a paper of Robin for the discrete case. What does this equality actually mean? So when I give you this definition of cost in terms of factor graphs and so on, I was stressing that the factor graphs should be deterministic given the input, right? Now what I'm saying is actually you're allowed a little bit of randomness as a treat. You're allowed factor of IID randomness. And yeah, this is not at all obvious that this would give you the same notion of cost, but it does. And you can do things with factor of IID constructions that you can't without. So another fact is that if you take any one of these Bernoulli extensions, these IID marked processes, then they factor onto the Poisson. So if you're familiar with the definition of the Poisson point process, or rather, if you've encountered it before, then you'll see why this is true. But in particular, this implies that the Poisson point process has maximal cost. So if you want to prove fixed price, in particular fixed price 1, you don't need to consider all free actions. You can only consider this very beautiful one, the Poisson point process. That's the only one you need to think about. So this suggests a strategy to compute cost. So to show that a group has fixed price 1, it suffices to show that this IID marked Poisson point process weakly factors onto an action with cost 1. Okay, so it's not really, I mean, you can try and think about why the Poisson point process on a group directly has cost 1, but even in the simple example of G times Z, I can't give you a very satisfying explanation for why it has these cheap factor graphs. But if I'm allowed to take another weak limit, which I am, then it is quite easy. So this argument was first used to show G times Z has fixed price 1. So in that case, groups of that form, they have obvious actions with cost 1, and it's reasonably straightforward to show that you can weakly factor onto them. Okay. Whereas for semi-simple Lie groups, the weak factor limit is an intrinsically interesting object, and it has cost1 for truly bizarre reasons. This is what I want to explain. Maybe in terms of the history, I should say something that it was known that you could define cost for actions of locally compact groups, but no one really did it because they couldn't prove any theorems. And one of the first most basic things that you would want to prove is that groups of this form G times Z have fixed price 1. And so that was like a stumbling block for a while. I don't know, is this correct? So, this is something that I proved with Mikołaj. And that's all well and good. It's just that groups of the form G times Z are not particularly spicy. Whereas these semi-simple Lie groups, this is something people actually care about. So, or at least I hope so. So now I want to talk about what this limit object is, the strange beast. And so I have to introduce a basic concept from metric geometry. That is the idea of Voronoi tessellations and Voronoi cells. So if I have some collection of points, some configuration.
Sorry, so now you want to describe this object that has fixed price, has cost1, and that you pick which big factor on them.
Exactly. Yeah, okay. That's the next task. So if you have some collection of points, then you can consider their Voronoi cells. This just means that each point kind of metrically claims everything closest to it. Okay, so I give you a kind of formal definition, but I think it's a reasonably intuitive object. And the Voronoi tessellation of a set of points is this ensemble of closed sets. Okay, so if you're sampling from an invariant point process and looking at its Voronoi tessellation, then this will be an invariant random tessellation of the space. So that's what we're going to do next. So this is the concept of the Poisson Voronoi tessellation, or PVT for short. So take the Poisson point process of some intensity, and then consider its Voronoi tessellation. Okay, this is the Poisson Voronoi tessellation for the intensity T point process. This is a very natural object studied in crystallography, calculation theories. It has applied, actual applied applications and so on. Yeah. So now I need to introduce something which is perhaps unfortunately named the pointless Poisson Voronoi tessellation. We did not christen this object, but rather some probability theorists, they asked an extremely natural question. I'm very surprised that it took until last year for it to be asked. What happens to this tessellation as the intensity tends to 0? Okay, so if you think about this, it means that now the cells are getting bigger and bigger. And so I claim that there is a limiting tessellation, and it's referred to as the pointless Poisson Voronoi tessellation. Okay, so it's an invariant random tessellation, and now all of the cells have infinite volume. I'll show you a picture of this thing in a second. Why is it pointless? It has no points, right? So when I look at the Poisson Voronoi tessellation, each cell is associated to a specific point, the germ of the cell. Now, when I take this limit, the points have disappeared, right? All I have is just these big cells. This is what they meant when they called it pointless.
But the point just went to the boundary, right? Somehow, so
you're ruining the surprise. Yes, I will explain this next. So here's a basic fact. So if this object exists, this PPVT, it is a weak factor of the IAD Poisson. So if you take the Poisson point process and you look at its IAD marking, you can do what's called independent thinning, where you delete points with some fixed probability. And in that way, you get the Poisson point process of lower intensity. Okay, so if this object exists, then it is a weak factor of the IID Poisson. I want to stress that it's extremely difficult to show that this object actually exists. This is a very, very complicated calculation.
So you delete points with some like equal point process, or?
So if you started with the Poisson point process of intensity 1 and you independently delete points with probability P, you get the Poisson point process of intensity P. And so, yeah. Okay, so here's a picture. This is from their paper. This is on the hyperbolic plane. Really what they've sampled here is the Poisson point process, or the Poisson Voronoi tessellation of some low intensity. And this is what it kind of looks like. The cells are colored black and white because they're doing independent coin tosses and coloring the cells black and white because they're interested in if this object percolates or not. That's the kind of thing that probability theorists do. So now I want to introduce.
So they prove that this limiting object exists for at least like on the street.
I think in a future paper they will prove this. They prove. They prove something about Cheeger constants of hyperbolic surfaces, and prove that these are bounded away from the Cheeger constant for the hyperbolic plane using this model. And they say in a future paper we will, I forget the exact wording. In a future paper we will discuss other properties of this tessellation. But strictly speaking, they don't prove weak convergence. But we do. Well, actually, no. I mean, we prove, okay. So let me introduce the actual object that we study, which is called the ideal PVT. So what we really compute is a slightly different random object, not a tessellation. That's something that we for now call a Horicon, and it is a weak limit of the IID of the Poisson. And associated to this Horicon is an invariant random tessellation, which we call the ideal PVT. Okay, so as Anush alluded to earlier, it's not that in this Poisson-Voronoi tessellation with the intensity going to 0 that the points disappear, but it's rather that they go to the boundary. And points on the boundary are usually called ideal. So this is why we refer to this object as the ideal PVT. If a certain continuity result is true, and we do believe that this result is true, but we're probably not going to prove it, then the IPVT and the PPVT are the same tessellation. But this Horicon, this is like the better object. And this is probably going to be useful for other applications anyway. This is really the thing to study.
So this comes with mark, because you said the IID of the Poisson?
Sorry, it comes with a mark? What?
Yeah, I mean, so why we go into the IID, so you're taking mark, or is that the term you use?
Marks labels.
Associated to the points, or am I?
You do get these points.
So what I'm saying is that there is some random object called the Horicon. There's two ways of thinking of it. So you can think of it as a point process on the space of continuous functions on the group. That's one way to think of it. And what I'm saying is that that object is produced as a limit of the IID Poisson point process. So the IID
Of factor?
Yeah, factors.
Oh, okay.
Yeah, so this object is produced as a weak factor of the IID Poisson, which is important because we want to talk about its cost. I mean, that's how we relate its cost to the cost of the Poisson. This stuff is all incredibly complicated, by the way. I don't know. I'm trying to make it seem slick and nice, but this is, you know.
So in this IPVT and PPVT, so there's like the proof PPVT exists, there's some object that you take, and then you don't use points in the boundary, and then you also.
No, so what we do is we construct this object, the Horicon, and we have an explicit description of it as a certain point process on the boundary times R. It's a Poisson point process on the boundary times R, the Maharam extension of this boundary. And so associated to that is a tessellation, and that's the tessellation that I call the IPVT. If this continuity result is true, then these two things really are the same. That would be nice because it would be easier to explain what this PPVT is. Whereas for now, I'm just being a bit vague. There is some kind of tessellation. It's called the ideal PVT. And it's, yeah, produced by taking a Poisson point process on the Maharam extension of the boundary. I can say more about it in private, but I don't have slides. Okay.
Is tessellation your technical term or just a not technical?
It's a random tessellation of the space.
What's the word tessellation?
So strictly speaking, the way that we, so strictly speaking, what we do is if you look at the Poisson-Voronoi tessellation, you can look at the boundary of the cells. That gives you a random closed set, and that's the actual way that we work with this. But so, I mean, the tessellation is a way of splitting your space into cells such that they only intersect at the boundary of the cells, right? So it's technically speaking like a cover of the space. So this is my attempt at sampling from this ideal PVT on the hyperbolic plane. I don't know how this looks on the. So it's kind of similar to the earlier diagram, except a bit more chromatic. if anyone is any good at Mathematica, then you can maybe help me get a better picture of this, but this is what I have for now. Of course, we're interested in the higher rank case, so not the hyperbolic plane. This is just so, you know, I can show you some pictures. Okay, so let me remind you the strategy for proving fixed price one. Because this Horicon arises as a weak limit of the Poisson, the cost of the Poisson point process and the cost of the Poisson point process times the Horicon. In other words, if you independently sample from the Poisson point process and this Horicon, those two actions have the same cost. So in other words, what this means is that when you're trying to construct cheap connected factor graphs for the Poisson, you're allowed to independently sample from this ideal Poisson-Voronoi tessellation and use that to construct edges, because it's a factor of the Horicon. So yeah. Strictly speaking, this pi times the Horicon is not a marked point process, as I've explained, but it's very easy to turn it into a marked point process. But this is the meaning of this equality. It's that if you're interested in constructing these factor graphs, you can sample from the ideal PVT and use those. So the factor graphs necessarily, they're going to have two types of edges. Edges which go inside of the cells and edges which go between the cells or between Poisson points in different cells. So what goes on inside of the cells? This is, to be honest, not the most exciting part of this. So I just, blaze through it. I claim that the induced equivalence relation on the Poisson is hyperfinite. This is maybe intuitively true because in this tessellation, the cells are kind of a limit of finite volume cells. So maybe it's not so surprising you end up with something hyperfinite inside of the cells. Although strictly speaking, our actual proof, I am not able to turn that intuition into an actual proof. But we use amenability of some associated action. This proof is not particularly enlightening, is what I want to say. And it's also not the interesting part. The interesting part is what goes on between the cells. No, I could not. I mean, maybe you can help. So the interesting thing is what is going on between the cells, specifically in higher rank. So this is the bizarre property that this ideal Poisson-Voronoi tessellation has. So I claim that almost surely every pair of cells in that tessellation touch a lot. I'm going to be a bit more precise about what this a lot means. So let me introduce something that I call the strict one wall. So I have a little cartoon image. So I'm looking at two different cells in this tessellation. And I want to consider, so strictly speaking, it's a tessellation of the associated symmetric space. So what I want to do is look at the set of points such that when you look at the one ball around them, it hits both of these cells, but it is disjoint from every other cell. Okay. So these are points close to the boundary of these two cells, but seeing no other points, no other cell. And so the meaning of what was on the previous slide is that almost surely the volume of those regions is infinite. Okay. So in this tessellation, every pair of cells is adjacent. Every pair of cells is adjacent, and not just like they touch and then they go away, but they keep touching each other. This is a very strange property. I don't know. Rukash said that this is what I should really be leading with in the talk. I don't know. It's yeah.
Where you use the head-on property.
Exactly. Yes. Okay. So once we have this fact, the proof is almost done. So how do I construct my crossing edges? So remember, inside of each cell, I'm looking at the Poisson point process. I have something hyperfinite. So I can construct a graph, a connected graph inside that looks like Z, for instance. Now I need to add in some other edges so that the entire graph is connected. And what I'm going to do is I'm going to independently sample from this Poisson point process. Those strict one wall regions, those are all disjoint by definition, and they have infinite volume. So that means that my independently sampled Poisson point process has to hit every one of them infinitely often. So this is my little picture. I'm looking at some pair of cells, and I'm looking at the strict one wall. And because I'm independently sampling from this Poisson, I can find infinitely many pairs such that one is in one side of the strict one wall, one is in the other, and the distance between them is less than 1. Now, if I take those as edges for a factor graph and take the union with what was going on inside of the cells, I have something connected. Right? You give me two points. If they're in the same cell, they're obviously connected. If they're in disjoint cells, then I can find one of these crossing edges and so the final trick is that I can then percolate those crossing edges and send their edge measure to 0. And so the average degree will be like 1 plus epsilon. So this is how you prove fixed price. I don't know. So are there questions about how this construction works? So yeah, the final comment that I'm going to make is that I hope that I've presented sort of the big picture of how this argument goes, and I hope it's reasonably clear. If anyone wants to hear any more details about this, I'm more than happy to talk about it. But this is not like an easy result. I don't want it to seem like it came across too slick or something like this. Like this is quite a difficult sort of thing. So yeah. Anyway, I finished that.
Let's say you can go over time.
Yeah, I don't know. It's
Okay, so other questions for Sam?
So this proof strategy seems like it'll work as well as long as like the transitive closure of this relation of cells having large boundary is everything, right? Like you prove the stronger thing that almost every pair has this large boundary in common. It's an make fun and then he jumps, right?
That's right.
Does this theoretically apply to a wider class of groups than these IRA, or is it basically the same thing?
I mean, the trick is really showing that this limit actually exists. That's, I mean, yeah. So if there is some class of groups that you are interested in, you can try and prove that this limit exists, but it would be quite difficult. I don't know. Yeah.
The hard work is.
In a certain sense, yeah.
Somehow is it automatic that it only exists and these boundaries would have to be, these touching boundaries would have to be?
We use other things about it. So we use that a certain subgroup, yeah, it would not be automatic. Yeah. We use that this limiting tessellation can be thought of as a Poisson point process on a certain homogeneous space of the group. So on some space of the form G mod U. And this subgroup U has the property that when you intersect it with almost any of its conjugates, you end up with something that looks like R to the rank minus 1 of the group. This is the key thing that we need.
R than real?
Yeah. But that's where the higher rank thing manifests. And so to have that identification, you also need Lie theory in order to, yeah.
And then what gives these infinite things?
This is a tricky application of the ergodic theorem. So I have to explain this argument to Wilkens and lattice and so on. So if you want to hear about it, that's, yeah. I don't know an easy way of explaining the class of groups to which it applies, but it's there's a certain class of groups that you could hope to prove fixed price 1 with this strategy, and it applies for all of them. So yeah. Yep.
So did you get any insight, applying this to something that doesn't have fixed price, doing it on the hyperbolic plane? Do you get any, or that has fixed price and not fixed price 1? So does it give you any insight to the cost, or maybe not that, to the L2 Betty numbers or higher?
Well, for the hyperbolic plane, we know the cost.
Yeah, but does your technique apply?
That would be a somewhat perverse way of going about it, right? I mean, like you guys prove strong treeability. That's like the.
No, I think the sense in which the geometry is similar.
Yeah. So we want to know if there's still information outside of the cost 1 from.
I mean,
Yeah, go ahead.
Well, so the bigger question I think would be, can you use this object to say anything about cost for hyperbolic free space? So conjecturally, this has cost 1, and I don't know what properties this object has there. That would be something that you definitely want to investigate.
And does this object also reflect anything about the L2 Betty numbers besides in the first degree?
I have no idea. That's something to think about.
But also because Poisson is the maximum. If you prove anything about that, unless you prove that it has cost 1, then it won't give you information about fixed price, right? It will just give you one, for instance.
But sometimes you can identify what the infemal cost is, right?
Yeah.
So and this is the supremum cost. So
So you said the idea to be really like pushing the points to infinity.
Yeah.
What if you actually sample points to the boundary and say pick some point in the space and then tessellate into that?
So that picture that I gave you, the way that I get that is I sample from a Poisson point process on the boundary times R with a certain, it's essentially the Maharam extension of this boundary. And that's that's essentially the way that we actually do it.
Other questions? Okay, if not, let's thank Sam again.